This particular talk is the second in the series, and it's being broadcast remotely from Ireland. This is the first time we've tried this experiment, and it looks like it should work well. If you have questions, please type them into the chat box, and then at the end of the talk, I'll go ahead and announce the questions, and we can address them to the speaker. Today's speaker is Dr. Andy Shaerer, Director of the Center for Astronomy in the School of Physics at NUI Galway in Ireland. Dr. Shaerer will be talking about high time resolution astrophysics in the ELT era, including science problems and detector requirements. Dr. Shaerer graduated from London University with a BS in astronomy in 1975. He then obtained a master's and PhD from Durham, worked as a postdoc and then in industry, and then came back to academia in '91 at University College Galway. In 2005, he founded the Irish Center for High-End Computing and was its first director. He's interested in high time resolution astronomical observation, modeling astrophysical plasmas, and medical and astronomical image processing. He's now director of the Center of Astronomy. So Andy, if you can go ahead and share your screen.
Okay, Don, thank you for that. Greetings from Ireland. I hope you can hear me. And I will start. This is a bit strange because I'm talking from my office and I understand there's more people there and a lot of people coming in remotely. So let's see how this works.
We can hear you very well.
Okay, great. Now, in some ways, I'm a bit of a fraud because I'm going to be talking about primarily high time resolution astrophysics, and I'm going to be talking about one or two case studies rather than the kind of specific detector technology. But what I want to concentrate upon is the impact the science requirements will have on potential detector developments and so on. The rationale behind that is that in the past, and we were also guilty of this, that a lot of the detector developments have been driven by detector physics rather than the requirements of the science. And what we'd like to do now is to say what kind of science we want to do and what kind of detectors will be required to actually achieve this science. Now, the research which I'm talking about has been done here and also in some of the partners to the Opticon network in high time resolution astrophysics, which involves most of the kind of major groups which are involved in European HTRA. So I want to go on and begin to talk about why we regard high time resolution astrophysics as important. And there's a very interesting document which is available on the web and it's available from my homepage called A Science Vision for European Astronomy. I presume there's been similar kind of documents in the US, basically sort of trying to set a kind of strategic framework for the next decade of astronomy. And in particular, where our interest comes from is what the discussions around Panel A, which was looking at the understanding of extreme physics. And it's those areas which is where HTRA can actually probably deliver its most important contributions. And this particular panel identified 6 different areas, and these range from how did the universe begin, and what is dark energy and dark matter, some very fundamental questions. Can we observe strong gravity in action? Basically tests of general relativity. How do supernovae and gamma ray bursts work, which is becoming down to the slightly more prosaic in terms of astronomical observations. How do black hole accretion jets and outflows operate? And I would extend that to probably just general jets and accretion that aren't understood completely. And then what can we learn from energetic radiation and particles? And when I looked at that list, realized that actually we can actually look at definitely the last 4. We do not address issues like how did the universe begin, unless there's some kind of some aspect of that which we haven't thought about. And certainly dark energy and dark matter isn't necessarily part of high time resolution astrophysics. unless again there's some aspect of this which we're not properly aware of. But certainly all the other aspects are involved in high time resolution work. In 2010 we held a workshop in Crete, and here's a list of the kind of topics which came up during that workshop, which came as a bit of a surprise because most of the organizers were either instrument developers or they're involved in basically this top group here, magnetars, pulsars, and neutron stars, which are the kind of astrophysics components which are the most challenging to observe. And when we looked at this, we actually had everything from effectively from black hole systems down to planet satellites and Kuiper belt objects like Pluto. So one of the interesting talks came from Vic Dillon, who's the developer of the UltraCam system from the University of Sheffield. And that's probably the most successful high time resolution astrophysics instrument which is around at the moment. And it uses the most conventional technology. It basically uses frame transfer CCDs in its normal imaging mode, or electron multiplying CCDs when it's working in its spectroscopic mode. And over the last 10 years, they've had a large amount of time on telescopes in the Northern Hemisphere, in the Canary Islands, as well as in the Southern Hemisphere in Chile, both on the NTT telescope and on the 8-meter Very Large Telescope, VLT. But over that 10-year period, they've identified these different areas ranging from accreting white dwarfs and cataclysmic variables coming in at 20%, and black hole, neutron star, X-ray binaries another 16%. And the reason for that large number of those types of objects is that UltraCam was designed to look at those kind of objects, all the way down to kind of occultations and transits, extrasolar planetary transits, and a few smaller objects, GRBs. They spent some time observing GRBs and so on, and quite surprisingly all the way out to active galactic nuclei have been observed. So it's a real gamut of potential astronomical observations have been observed at this kind of less than 1 second, less than 10-second time scale. Okay, the questions which I want to address during this talk are, or in part, are the following 4 questions, and I won't be, there's not going to be equally spread between these 4 questions, but we're going to actually look at what's the kind of current generation of astronomical instruments and telescopes, what kind of results are coming from them, the future developments. The 30 to 40 meter class telescopes are going to come on stream around about next 10 years. 2020 has been the timescale for the European Extremely Large Telescope, and these are the kind of instruments where hopefully HGRA will come into its own. The next and really important question relates primarily to the European Extremely Large Telescope and not necessarily to the 30-meter telescope in the US, is that the ELT's optimal wavelength is around 2.2 microns, whereas the current generation of detectors are kind of looking primarily in the optical from about 0.35 microns up to about 1 micron. And clearly, if we move into the near infrared, there are going to be quite significant implications about what kind of science we can do, and also the way in which the detectors work. And the 4th question is, what kind of science do we want to do? So that would be, I'll be concentrating slightly less on that, but mentioning that in passing. Multi-wavelength HGRA is really important, and the prime reason for this is that when we begin to look at objects, it's a real mistake just to say we're going to be an optical astronomer or we're going to be an X-ray astronomer. More accurately, people should be describing themselves as, say, neutron star astronomer or close binary system astronomers. And you need observations at high time resolution at all wavelengths. The problem is that fast timing is a natural component of radio observations, X-ray observations, and gamma ray observation. It isn't for optical systems. Most optical cameras in kind of observatory systems don't have the required software and data pipelines and hardware to actually observe accurately at absolute timescales less than about a tenth of a second. Excuse me. Now, one of the problems which we discussed at the CREEP workshop is when is high time resolution, and when is it just kind of normal observations? And in some ways, this is set by the detector technology. And until recently, we would have a kind of time scale of somewhere between 1 and 10 seconds would be the time when you kind of move from normal systems into high time resolution systems. One of the suggestions which came from the CREEP workshop was that possibly we should consider the dynamical timescale. That is effectively the astrophysics of compact objects, and the dynamical timescale effectively being the free fall time of an object, the collapse time of an object, which would be given by basically 1 over the density. And for a white dwarf, the dynamical timescale is roughly a second. And this has got to be compared to the other timescale, which is the light crossing timescale, which is about 20 milliseconds for a white dwarf. The other suggestion is we should just stick to some arbitrary time of timescales of 1 second. My preference, and I'll justify this over the next 40 minutes, is that HTRA is effectively low noise observations, and that's the thing which distinguishes it from other observations using kind of conventional techniques of CCDs and so on. And hence, the problems associated with high time resolution astrophysics becomes a detector problem rather than trying to fit in some kind of arbitrary time scale. And I'm going to be sort of coming up with justification for that. It's worth, in the context of high time resolution astrophysics, looking at this this paper, which is on AstroPH. It's also on my homepage, not because I was the first author on it, but because it's a kind of summary of the Opticon network's activity over the last 5 years. And we tried to kind of bring together the different aspects of high time resolution astrophysics into one kind of heading to see where the science was going, and hopefully use this as an influence on the design of some of the instrument payloads on the ELT. What I've got here on this slide here is in these first 2 columns, the kind of astrophysics which is being discussed, and in the second 2 columns, the timescales with which we can observe these phenomena now with the kind of 4 to 10 meter class telescopes, and the timescale in the kind of 30 to 40 meter timescales. So these are kind of rough kind of figures. Now, when we talk about timescales here, we should also consider what the photometric accuracy is going to be, and in some cases it's going to be problems associated with photometric accuracy, i.e. how bright these objects are going to be, which will determine whether they can be properly observed. And we can actually look at stellar flares and pulsations on timescales of seconds to minutes now, and we can presumably begin to look at structure within flares, stellar flares, on timescales of 10 to 100 milliseconds, hopefully in the ELT era, looking towards the kind of the near infrared. One area of interest is stellar surface oscillations of white dwarfs, kind of astroseismology, which we should be able to see timescales between 1 to 1,000 microseconds, 1 to a millisecond, 1 microsecond to a millisecond. And we can observe these now, but the advantage of the ELT era is that we can go down to fainter objects and actually get better photometric precision and a better understanding of surface oscillations, and consequently a better understanding of the internal structure of white dwarfs. The same can possibly be applied to neutron stars, so I think this is really a very optimistic statement here. That will certainly be 100 nanoseconds is the timescale on which we'd expect a neutron star potentially to oscillate. But whether, given their intrinsic optical and near-infrared faintness, whether they'll be able to observe this even in the ELT era remains to be seen. Close binary systems, there's a lot of work which can be done on timescales of the order of milliseconds, and as I said before, UltraCam was designed to observe in this kind of time frame. And in the ELT era, we should be able to go down to timescales of less than a millisecond, or to have very accurate measurements up to the kind of 1 second scale. Pulsars, which are the objects which probably begin to stress most detector development the most, magnetospheric observations, we can begin to look at timescales which range from microseconds down to nanoseconds in the ELT era, and potentially looking at thermal variations, either thermal variations of distribution, temperature distribution of debris disks, for example, around some neutron stars, and or surface temperature fluctuations. We'll be talking about timescales of the order of 100 milliseconds to milliseconds. AGN, minutes to seconds, timescales can be observed, and whether that falls under the auspices of HDRA is a separate question. For this slide here is probably one which is of more interest to this particular group. Here is a kind of snapshot of the current detector capabilities which are available. This is unashamedly kind of Eurocentric in some regards, with the possible exception of the TES detectors and the kind of microwave kinetic devices here. What I want to do over the next few slides is to go through these different detectors, and I want to concentrate on a number of different systems which have been used. I won't go into systems, for example, like LuckyCam, because I know Craig Mackay is giving a talk later on about this, and I'll only mention in passing the superconducting telescopes, the STJs, the transition edge sensors, and the kinetic devices down here. I want to concentrate primarily on things like UltraCam, the GAUSS, which is our own instrument, the two main APD systems, which is Optima and iQuai, and I want to actually put some of their results into context. So to start off this process in terms of what can you do with a straightforward frame transfer CCD, to me, and I'm slightly biased here because I was involved in this work, one of the best results which came out of UltraCam was this observation here, and you can see this kind of little, what seems to be an artifact here, is in fact a magnetar. It's this X-ray object here, and it's basically it's otherwise known as anomalous X-ray pulsar. It's a very slowly rotating neutron star with a period of a few seconds, and it has an extremely strong, potentially an extremely strong magnetic field. And here are some observations taken on the WHT by UltraCam, and you can see over a few frames here that the intensity of this object seems to be varying slightly compared to this one here. And what we have here is with UltraCam that this is showing part of the full frame image which they were recording, because they could actually record fairly slowly because the period was only was a few seconds. But at the kind of the level of about 25th magnitude, which is probably measuring about about one photon per revolution of the star, over a number of different hours of observations, you can begin to get something which shows that this is varying. And down here we see the light curve. We see when we've been all the number of the several hours of observations into what's a recognizable light curve. And here's an average of that light curve coming through here. This is a kind of typical pulsar light curve which has been repeated twice. We can see two phases of this, and this is an average light curve. So this frame transfer CCD is capable of observing these kind of relatively slowly rotating objects, and even down to objects which are as faint as this particular magnetar at 25th magnitude. Other attempts to observe this have involved using CCDs, where basically the imagery is being binned up on the chip. But in the case of UltraCam, it uses the frame transfer to be able to read out all of these different images. The next class of object I want to look at is pulsars. And I'm showing an image here which is now about 15 years old, which we took using in fact I think it was taken using the STIS ground-based MAMA detector. So it's a photocathode-based system with a time resolution of about a millisecond. And what we see here is part of our images which have then been binned up in phase with the pulsar period. And we see the pulsar in the center of this field flashing off compared to this nearby reference star. So that's the kind of objects which we're looking at. The crab pulsar itself rotates about 30 times a second. So we need obviously very high time resolution to resolve its light curve. In order to do this job properly, sorry, we need a faster system, and the system which we've used recently in association with the University of Padua is their IQI system, which was designed to, you see the kind of time resolution here is 100 picoseconds, which is what they're trying to get in terms of their absolute timing. And certainly the relative timing is down to that kind of scale, using GPS and their own atomic clocks to actually integrate these together. So what we have here is the ability to actually look at the objects like this on much faster timescales. And we can then produce plots which look a little bit like this. We've got the crab pulsing away here to remind me what's going on. And what we see here is the results of 4 nights observations with IQI. And what we see here is the pulsar phase split into in 2 phases, averaged over the 4 nights. And we can see that we get a bright flash of light and then a dim flash of light. And that can be seen here. We get the bright flash of light followed a little bit later by the slightly dimmer one. At some point here, the pulsar seems to switch off completely, although that's a slight matter of contention. But to show the importance of this in terms of the timing accuracy which is needed, I put up here the Jodrell bank ephemeris, which is required to fold this data together. And if it was the kind of thing which was given to me in an undergraduate lab, I'd probably give them a lecture on significant digits and so on. But in fact, most of these digits are required to produce the right level of folding of this data over the 4 nights of observations. The other aspect in terms of this inset here is that the peak of the crab, you can see here, just arrived before the radio. The phase 1 is when the radio pulse arrives from the pulsar. And what we can see is that the crab arrives slightly earlier than the radio pulse, with a width of about 33 microseconds, but the radio is delayed with respect to the optical, or the optical becomes first, with a delay of about 178, and I think the error on that would be about plus or minus 10 microseconds. So I'm going to come on to this kind of data later on when we talk about pulsars as a science case, but that gives you an idea of the kind of work which will deliver important results in the future. The next instrument around is Optima, which also uses avalanche photodiodes, photon counting avalanche photodiodes, again single pixel devices. And here's this result, again on the crab, taken with Optima. And what we see here is the main pulse which we had before, but on top of this they have also measured the polarization, and we can see the polarization angle swinging, not necessarily in the way in which intuitively you might expect it to. And down here we see a plot of the polarization degree, and what we see is that the degree of polarization peaks very strongly prior to the main pulse coming through, which is an unusual result, which again we'll talk about in a little bit more detail later on. And I should note with the crab, there seems to be a high degree of polarization away from where the pulsar is working, and this is because very close to the pulsar, about half an arc second away from the pulsar, there's a very bright synchrotron knot, which is highly polarized, and it has the same polarization characteristics, for example, as the gamma ray polarization, which has been measured by integral. Now, I do want, we've mentioned the CCDs and 2 APDs. I'd like to sort of talk about what's coming on in the future, and this is these kind of superconducting detectors, which are probably going to be some of the most exciting instruments available, certainly on the ELT, hopefully when it comes along. And I've taken this from one of the Archon's papers, and here you see a simulation of one of the very few optical pulsars. This is the 26 magnitude object, really faint. The best definition I know of 26 magnitude, it's about the same flux you'd expect to get from a candle on the moon. So clearly it's pretty faint. And what they've got here is a simulation of the expected spectrum they might observe with a 2.5-hour Keck observation with their energy sensitive detector, and they've compared it here with the similar observations taken with the CCD and integrated over a prolonged period. And you can see that in a 2.5-hour observation, they've got a reasonably significant spectrum has been measured, and they've artificially put in a cyclotron emission line, and that should be detectable fairly readily with that kind of system. So I think this is going to be the future, and I think the next talk in your series will be of the superconducting telescopes. So I'm mentioning that as being something which is really quite an exciting development coming up. But back to what we can do already, the multi-wavelength observations, X-ray and near-infrared of close binary systems are very important, particularly when you begin to do correlated observations. And again, this is the importance of being able to take simultaneous observations in an optical regime, or in this case an infrared regime, and in X-rays. And here we see some observations of a black hole binary system, and here is a cross correlation of the optical and of the X-ray and near-infrared flux. That what we can see here is in X-rays, these objects flicker as material moves from the donor star onto the primary star. And here we see the similar kind of light curves being followed in the infrared. But when we do a cross correlation, there are interesting lags have been observed and interesting degrees of correlation. And we can actually see the width of this correlation then gives us a lot of information in terms of the orbital characteristics of the system. We move on, and there's observations of another X-ray binary, and the reason I put this plot up is to look at the kind of, again, the correlations between the cross correlation and the lags which are around, and we see lags of the order of a few tenths of about a kind of maybe about a 50th of a second coming through, 20, 30 milliseconds. So clearly we need absolute timing of that kind of scale in order to actually measure those lags effectively. And then when we begin to look at these kind of plots of the phase lag against the frequency, and these are of kind of random flickers which are going on, that we're beginning to lose information at this point here. And it'd be quite interesting then to compare and to begin to look at quasi-periodic variability on time scales between 1 second down to a few milliseconds. And again, the detector implications from that are quite extreme, as are the system implications, and to make sure that we've got the absolute timing capability to do these cross correlations of simultaneous observations. The next observation is going from kind of very distant objects in terms of very unusual objects, close binary systems, to another fairly exciting ultracam result, which is unexpected, which is observations of Titan. And what they did here sorry, was to look at Titan as it moved in front of this star here, which has the lovely name TYC 1343 minus 1865, and to look at that occultation and basically to see whether the information which comes from the light curve of the occultation, which can be seen here, gives information about the atmosphere around Titan in terms of the expected temperature distribution, pressure, and so on. And what we see here is the light curve in 3 of the ultracam simultaneous bands, IG and U. And what we see in the infrared, we see this nice peak, which is expected because the infrared can actually be absorption in the infrared can obviously be transmitted further through the atmosphere of Titan. And what's very nice about this observation is if we compare this central peak here on a much shorter time scales and compare it with the expectation of various models, you can begin to see that there's actually quite a nice correlation between the expected peak here and the dotted lines, which are the kind of light predictions. But these type of observations can give very almost unique understanding of what the atmosphere of these kind of distant objects within our solar system, and hopefully in the ELT era, similar observations of occultations of exoplanets might begin to give the same kind of information, albeit in a slightly more photon-starved regime. So transits, again, are very important, and the speed of the transit, again, gives us a lot of crucial information about the geometry of the system. Now I'm coming to the question of what is the ideal HDRA detector. And the important thing here is the word ideal, and I can appreciate that my wish list is probably never going to be given. I had a very interesting comment from one of the optical designers here, a Russian, who we were talking about trying to build a new type of telescope which just points up at the zenith, and I gave him the science drivers for what this telescope should do, and his comment was that this is a typical response from an astronomer to come up with things which are absolutely impossible. And in some ways, maybe the ideal HDRA detector would fall into this category. The first aspect is that it's got to be low noise, and low read noise, and I would say that there should be less than 1 electron per spatial element and less than 1 read noise per temporal element as well. So that is something that's to be achieved, and in some ways this has already effectively been achieved with electron multiplying CCDs, albeit with possible problems in terms of quantum efficiency, and possibly with devices like SCMOS devices, but certainly a certain number of photocathode-based systems and APD-based systems do satisfy that criteria. Should be capable of fast timing, and by that we mean either one of these three things. For a millisecond for most applications, and fairly conventional detector systems can actually achieve that. Times to microseconds for pulsars, for example, is achievable now. And then quite an interesting effect which could come on board when we get to the ELTs, when we have large enough detectors, is basically quantum effects. There'd be photon bunching effect, second order quantum effects, rather than intensity fluctuations, which can be observed, and they come in on picosecond timescales. And this was one of the driving forces behind IQI, for example. The next is there should be some energy resolution. It would be much better if we could build an instrument which doesn't require broadband filters, because we lose and cut out light at that point. So an energy resolution of E over delta E greater than 5 would be great to try and have that, something on those lines. And that indeed is possible with even the current generation of superconducting telescopes. And in particular, having superconducting instruments which don't require the electronics to be at helium temperatures would be quite a benefit as well. The spectral range should be in the range, say 0.35 microns up to 2.5 microns, certainly for the next generation of ELTs, to take full access of the adaptive optic systems, which are going to be around those systems, will be quite important. That 2.5 microns means that we're basically going into kind of presumably germanium rather than kind of silicon-based systems. Pixels. Now this is where we can actually relax the criteria. Is that for high time resolution work, we don't actually need a large number of pixels. This is not doing extragalactic surveys. 100 by 100 would be fine, depends on the size, as most of effectively our objects are point sources. And consequently, what we require is our target, and maybe particularly in the infrared, background information about fluctuations in sky brightness or nearby target stars, comparison stars. And then finally, this is the one where I think that my concept of ideal is being stretched a little bit far. I'd like to see polarization sensitivity within a detector. I appreciate getting energy resolution was difficult enough, and maybe getting detectors which are intrinsically sensitive to polarization without external optics would enable us to go even fainter. One of the problems we build a polarimeter here is that we throw a lot of the light away in trying to dissect the light, and in particular, if we can actually be able to measure linear polarization directly, possibly with these superconducting detectors. And the reason of the driving force behind this is that HDRA science satisfies one of the rationales behind the European Extremely Large Telescope, and I presume the same can be said for the 30-meter telescope, is that we open up a new parameter space. And if we had detectors like this over the next 10 years, then we'd certainly be in a position to open up a newer parameter space. The current, I mentioned in passing, I'm going to skip over this, the main instruments which we observed in Opticon in terms of doing science were these ones. They're all optical out to about 1 micron coming through. I mentioned those instruments which were specifically designed for HTRA purposes, and compare them with general purpose instruments. And what happens here is that it's realized that detectors can act fast, and the HTRA aspect is then put on often as an afterthought. And that means that we actually have problems then in terms of the timing capability of these instruments and in terms of the data pipelines which are associated with them. So what we'd like to see is the HTRA component is actually built into the system from the word go, that we actually know that timing is coming on board. We have the data pipelines which are available to handle the extremely large data rates and so on. And there are a number of systems which are available. These top two are from the on the VLT with timescales down to 3.2 milliseconds and 30 milliseconds, but the read noise here can often dominate what's going on, because with read noise greater than a few electrons, then at this rate, for example, this would be equivalent to a read noise of about 900 electrons per second. Salticam, again, fairly conventional technology with a read noise of the order of about 3 electrons, similar to Ultracam. And what happens then is that the read noise dominates at fast frame rates and limits the kind of time resolution which you can do. And this other point, which I can't stress too highly, is that the HTRI data pipeline is often an afterthought and quite often doesn't quite work as well as we would like to, or as well as it's quite capable of. Looking at the sky noise and read noise, is that the limiting factor in any HTRA detector is at which point does sky noise dominate and at which point does read noise dominate. I've got a plot here, I hope I got my numbers right, where I've basically got here counts per second per resolution element for a 10-meter class telescope and a 42-meter class telescope. And I've assumed here a kind of system quantum efficiency of the order of about 30%. That's allowing for atmospheric absorption, detector quantum efficiency, throughput through the telescope and so on. And what we see here is that, firstly, that the ELT range is round about here if we're going to take full access to the adaptive optics. Otherwise, we're down in this regime here. These numbers relate to obviously the size of the telescope and the effective seeing, 1 arc second, half an arc second, 0.1 arc seconds, and 1 milliarc second, which is probably the absolute limit for the ELT. And what we see is that clearly we are sky noise dominated completely for the 42-meter telescope with natural seeing. As we move down to 0.1 arc second, we're beginning to get down to counts below this line here, which is 1 electron per frame per kilohertz. And when we move into the extreme adaptive optics regime, then clearly we're going to require and need extremely low noise detectors. I should note that we're actually, this is where we are now in the visible. We're in a regime with basically 10-meter class telescopes, and we can actually go down to kind of time scales of the order of a few tens of milliseconds with conventional instrumentation. So this is where we are now, but this is where we want to be in the future. We want to be below this 1 electron per frame at 1 kilohertz and be able to actually explore this kind of parameter space. And effectively put some of these things into numbers for milliarc second imaging in the near infrared. If we have, this is the number of aperture counts within a kind of resolution aperture for 1 arc second, 0.2 arc second, 0.02 arc seconds. And these are the number of counts which we're getting per millisecond within there, and that's going to be the limiting factor. This is from the sky, and it's clearly our read noise has got to actually be less, significantly less than that. And in this case, we've also got to think about our dark noise from our instruments and our telescope at the same time. Why do we do HDRA now and into the future? But basically, over the last 10 years, low noise detectors have become available. The MCCDs, SCMOS, APD single pixel devices, all with very good and high quantum efficiency. When I started in this field, we were talking in some cases of systems which had quantum efficiencies measured in the range 1 to 5% with conventional photocathodes. Larger telescopes are available now, GTC and SALT in the northern hemisphere, GTC, Grand Canyon and Canary Islands in the northern hemisphere, and SALT in the southern hemisphere are all working. Gemini, Keck are all there, and we have 30 to 40 meter class telescopes planned. So we actually have telescopes which are capable of detecting the flux. There's a much bigger HDRA community now, and it's growing, and there are more multi-wavelength opportunities. LOFAR, Fermi has revolutionized pulsar astrophysics, and ALMA will probably do the same in terms of the number of different slightly cooler objects which it's going to be able to observe. What I want to do now, if I'm okay for time, is what we can do now, and I want to use optical pulsars for this kind of observation in terms of the science which we can deliver. And I want to look at observations by two optical groups, Optima and IQI, and the GARS group, which I'm involved in, have also observed with Optima and IQI. So that's where we're coming from. But in order to do this, I'm going to give you a kind of quick rundown on pulsars. This is kind of pulsar 101 on the P dot diagram. And basically, the period pulsars are a rapidly rotating neutron star. And the two things which we observe are how fast it's rotating and how fast it's slowing down. And then when we plot these, we see a great big bunch of stars here, and we see some which are down here, and there's a little population which is growing, which is up here, which are these are normal radio pulsars, these are magnetars, and these are millisecond or recycled pulsars, with periods of rotation ranging from about 1.6 milliseconds up to a few milliseconds. So that's the kind of, these are primarily, there's about 2,000 known in the, measured through radio observations, and these ones up here primarily through X-ray observations, these ones down here through radio observations. We can actually begin to do some work on this. We can plot out the number of these objects which are in supernova remnants, and what we see, the supernova remnants tend to be clustered around here, and these lines here refer to what's known as a characteristic age. We can work out, given how fast they're slowing down, how fast they are, what the location, what their kind of birth period was. And we see that the younger ones tend to arrive in supernova remnants, which is maybe telling us something. And the other thing is that we see these millisecond pulsars. There's a lot of them can be found in globular clusters. Maybe this is telling us something as well. High energy pulsars also tend to be up at this part of the diagram. They tend to be young. And notice also that these ones here, these magnetars, are also high energy objects as well. And the crosses here are anomalous X-ray pulsars. And here we see these new objects called RITs, which stand for rotating radio transients, which are pulsars switch on occasionally. Okay. Let's have a look at this, and basically what does this mean? That basically pulsars are born fast, they kind of go through middle age, and they reach what's known as a death line when they stop being pulsars, and then those ones in binary systems get spun up. The other thing which we notice is that we have these magnetars and we don't know what's happening about them, and there's a possible suggestion that there might be some movement along this plane from normal pulsars up to the magnetar area. But what we don't know is how they work, what's the birth rate of neutron stars, how many type 2 supernovae end up as magnetars, and then how do magnetars work. None of these questions we actually really know what the answers are going to be. So how can optical pulsars help? Here are the optical pulsars. Pulsed optical emission of these triangles here. There are very few of them. We plot this not in this way. We've got period-period derivative. We can actually begin to plot out where the optical pulsars are going to be. But a better way of doing this is to possibly look at how much this kind of strange unit here, which takes SI units and puts them on the head, ergs per second per square kiloparsec, is the kind of effectively the energy available to us. It's a fluence, it's a flux of some kind. And what we see is that the ones with the highest fluence are also likely to be optical pulsars here, and here we see the 5 optical pulsars which have been observed. Another way of looking at this is to estimate what the magnitude is going to be. And what we see here are the optical pulsars, and there are a few magnetar ones down here, and there are these ones here. And then the Fermi pulsars, the ones which have been observed by Fermi, we can see these crosses here. And I marked on here what we can actually see with a 10 sigma VLT exposure and an ELT 10 sigma exposure. I should stress that I put estimated magnitude, and if I was honest, that was a wild guess magnitude, which is here. But the limit here for observing these objects is, say, for example, that line there corresponds to about 1 d photon per second per Keck telescope. So these objects are faint, and that presents us with a problem. Here's the current known optical pulsars, and this is how many photons we get from them. And here's how many counts once we put this through an instrument, both in the VLT era now and in the ELT era. And the important thing to notice is that only one of them, the crab, has a sufficiently high flux to do anything realistic astrophysics now, and really maybe only one in the future will actually only have, maybe Vela as well, have a sufficiently high flux. And it's for this reason, quite often in the past, people would build an HDRA instrument, look at the crab, and think, that's great, we could do a lot of work with that. What other pulsars are there? And then begin to get a little bit disillusioned because they're all fairly faint. So moving on, I can appreciate I'm running out of time here. Observations which we can tell, we showed these earlier. We see the kind of the optical pulse here with IQI. IQI itself is primarily a timing instrument with a lot of avalanche photodiodes and rubidium clock and a GPS unit to give us absolute timing. Quantum efficiency about 30%, count rate, maximum count rate 8 million counts per second. But its accuracy, relative accuracy, is about 100 picoseconds, which is pretty impressive. We took some observations with Jodrell Bank, and here we see where our observations were with IQI, and here we see the Jodrell Bank observations. And we were looking at giant radio pulses. This is when the pulsar emits a lot of information, a big pulse in the radio. And with one night and in fact 2 hours observations, we could begin to see quite a significant 4 sigma effect, which was replicating some observations which we took earlier. And hopefully when we begin to analyze this data, we can actually have a more significant correlation between giant radio pulses and optical giant pulses coming through. I'm skipping over a little bit here, I appreciate the time. The crab Optima observations also looked at the polarization, as I said before, and the interesting effect was that when the crab, the main peak of the optical didn't occur when we have a lot of optical flux. It actually occurred when the radio pulse, radio precursor occurred, which is a little flash of radio waves which occurred just before the main optical pulse. I've looked at the Optima data, and where we see that optical radio pulse, we see no change in the intensity, but we do see a massive change in the linear polarization at this point, but no change in the intensity, which means that, to my mind, what gives here must be the, here we see a change in linear, but we see no change in the intensity, so there must be a change to circular polarization at that point. And this was really nice because it fitted in with some simulation work which we did. And this is the importance of HTRA to the pulsar community, and particularly polarization. Here we see a cartoon whereby we see the pulsar with its magnetic field, and this arrow here is the change in viewing angle if we begin to look at the pulsar in different ways. And what we see here is plots of intensity, but the important thing is this is what we see when we see the Stokes Q and U being plotted and the position angle and polarization. And from this we can actually then map out what, given a particular set of observations, where does this light come from? And this is quite new, and when we did this, we mapped out and we could begin to see that the emission was actually coming from a point which is about 300 kilometers above the neutron star surface, which was a bit of a surprise because a lot of people expected it to come from around this region here, a long way from the neutron star surface. Both when we looked at one pole of the pulsar spinning around and at the other pole, we saw this consistent view that the emission was coming from the neutron star surface. And it seems to be coming primarily from near what's known as the last open field line, which is good because that's where we expect it to come from. And then, quite dramatically, when we began to look at this in more detail, we saw that the emission here is what we've done here, taken observations, compared them with our simulations, and decided, and from that could reverse engineer the location of the emission of the pulsar. We can begin to map back and see that the emission occurs in a ring about 300 kilometers above the neutron star surface. Now, this was possible with two things. One, some pretty large computers with its associated quite smart software, but also the ability to take observations of, in this case, a reasonably bright object, but at a very high time scale, a few tens of microseconds time resolution, combined with polarization. And it was those things combined which enabled this kind of color mapping. And we hope in the future we can do this with other pulsars, but to do this we need better detectors with higher quantum efficiency, bigger telescopes in order to get our photon fluxes out, and then hopefully we'll be able to talk about comparing optical observations of optical pulsars with gamma ray pulsars to achieve the same kind of work. And the important thing is that we have these low noise detectors to enable these very, very fast observations. And finally, as an advert, here's GASP, Galway Astronomical Stoke Polarimeter, which is an APD device or using either CMOS or L3 CCDs to image the four beams which give us linear and circular polarization. And our final test will be in 3 weeks' time in Liano, and then the plan is that it goes to Panama, spelled rather strangely, in April 2012, where it will stay for a year to measure the polarization from, hopefully from magnetars and from normal pulsars. The conclusion I've got is HDRA can deliver very important science and can address the 4 of the 6 extreme physics questions which the Astronet panel looked at. But to do this we need fast, low noise detectors, large telescopes, excellent data pipelines, and I can't stress more that HDRA has to be built in at the design phase of these and at the instrument phase, and we need these near-infrared detectors up to and beyond the silicon limit are going to be needed. So with that, thank you. And I've addressed this in terms of the science, and hopefully I'll be able to follow the rest of these workshops to see how detector developments over the next kind of 10 years will allow us to deliver this kind of science. So thank you.
Okay, let's thank Andy. Hopefully, Andy, you can hear the applause. I just turned on the
computer
microphone
without realizing whether you can actually see what was going on.
Yeah, I guess it would be bad if we had said that the microphone hadn't been on the whole time, but we heard every little bit of it, and it was excellent. I did have some
I can see the first one.
In the chat window. I don't know if you can. Yeah, and I could just read them also. I wanted to know what the status was of the HDRA activities in Europe, because there was a focus research project.
Okay, I mentioned Opticon. And basically, Opticon is an EU-funded program for it's an optical and infrared piece of strategic infrastructure. It's actually combining it's, I'm trying to think of the right phrase, is developing the optical and infrared capabilities of European astronomy. And it's got a number of different strands. Recently, it's been primarily focused on delivering the kind of science case for the European Extremely Large Telescope. It's also giving access to, on one level, it's working particularly on adaptive optics. There are a number of networks which are associated with that, one of which is the high time resolution astrophysics network. The status of HTRA activities is that there are about 4 or 5 groups who have their own instruments which have active research programs, and these are the ones which I put my talk up there, which I mentioned near the beginning of the talk. We have these ones here. We have the Ultracam, Optimum, and iCline, the 3 main instruments which are actually in use consistently and observing every year. We have the new on gas, the Galway instrument, but all of these are optical out to about 1 micron. And does it have an influence on ELT instrumentation? The answer to that is yes, I hope so. The final instrument payload for the ELT has not been completed. It is likely that the first light instrument will be an infrared, low-resolution infrared spectrograph and imager based on the Mikado program. I can give a link to the Mikado instrument. It's developed at Max Planck in Garching, in fact. And we've been in discussions with them, and it's likely that there will be an HTRA component to that, either as part of their normal detector payload for the instrument, or we will build a separate HTRA instrument parasitically to exist within their cryostats. The thing about these cameras is that they're absolutely enormous for the kind of 42-meter class telescope, and they could easily put up with the small HTRA instruments, which tend to be quite small, even within their cooling system. As long as we can work at minus 170, the whole lot can work about minus 170, then we're fine. And another question is the X-ray domain interesting? Yes, very. There's a lot of synergies, obviously, between X-ray astronomy and optical astronomy. And what's interesting is the way in which X-ray polarimetry, for example, is becoming possible. And it'd be very interesting then to do simultaneous X-ray and optical polarimetry observations. So clearly, most of the people who are involved in things like Opticon are also involved in X-ray observations as well. Does that answer the questions?
Okay. Yeah, so that answered the questions I had written down. But I had another one also. You didn't touch very much on potential fundamental physics that could be addressed. Physics of photon statistics at picosecond and nanosecond timescales. Is that going to be possible with the ELT?
There are 2 problems there, and this is one of them is a problem which is going to affect all HTRA observations. The ELT has 5 mirror elements. They're obviously the primary mirror, secondary mirror, but it has 2 active mirrors. And it's going to be the behavior of those 2 active mirrors in terms of the control circuitry. They're active and adaptive. And clearly the control systems of that will introduce some measure of a timing signal. Now we've done some simulations, not on the ELT, but on one of its predecessors in terms of the design of the European 50-meter telescope, Euro 50. And basically the continual movement of the mirrors introduced an unwanted timing signal into, and that was a problem to try and remove when we did some simulations of different pulsars. Now, that's also going to have an impact on what I think you're asking about is things like kind of quantum correlations and so on. When you begin to talk about the physics of the photon arrival times, for example, and intensity fluctuations on picosecond plus timescales. And certainly there, you want to make sure that all your path lengths are accurately known at the kind of millimeter and sub-millimeter level. And whether that would be possible in the ELT is an interesting question. I personally don't believe that it will be, but the simulations and the work needs to be done to see whether the kind of quantum work which is being talked about, particularly by people like Dennis Dragons, is going to be possible with the ELT. The fluxes will certainly be large enough and high enough. But it's a question about whether the instrument, whether the detectors, the telescope optical configuration will be stable enough. I hope that answers your question.
Thanks very much. Yeah, I wonder if there's some sort of mode that they could put the telescope in where it's not quite correcting as much and it's just behaving like a light bucket. And then you could just take a big photometric aperture.
Absolutely.
Do photon statistics, but I'm sure that introduces noise also.
Well, we've asked ESEL on that, and it's actually an interesting point. What we've done is we looked at, for example, the VLT and the adaptive optics system, which is on the VLT, and looked to see how often it was working when it should be. And basically, they had a kind of roughly 20–25% of the time could the adaptive optics work according to its specification. That means that basically 75% of the time it was working as a natural seeing instrument. And the same kind of figures, maybe the split might be 50–50, will be working with the ELT, is the longer the time it will have to work as a natural seeing instrument. And our argument is at that time you can do interesting spectroscopy, clearly, but it'll be at a time when it will work as a kind of 40-meter light bucket. The problem is that none of the optical engineers liked it to be described as a light bucket.
Yeah, you need a fancier name, I think. Okay, those are all my questions. Are there any questions here in the room or online? I think I saw Zoran was typing, but I'm not sure if he had a question. Okay, that's fine. Let's thank Andy again, and we'll send out a link where the talk is archived to send it to.
Okay, it's been a pleasure.
So thanks very much, Andy.
Okay, thank you, Don.
Okay, signing off.